dive right into session 3 now, which is Key Energy Projects and the Technologies Part 2, moderated by Michelle Perez, who is the Sustainability and Energy Director at UC San Diego. Whenever you're ready, Michelle.
All right, thanks. I'm gonna share my screen. All right, good afternoon, everyone. It's been a good day of presentations. Welcome, hope everyone had a good lunch and enjoy that music. Session 3 today for this energy session, we're going to be talking, part 2, establishing models for energy storage programs. And energy storage is another tool in our toolbox for energy managers to deal with cost optimization, decarbonization, resilience. It's really important. We learn a lot of different strategies that folks are looking into, and a part of the solution is to incorporate energy storage in that. So I'm really excited to have some of my colleagues here today to talk through some models and lessons learned. And why this matters, we're all dealing with the same issues, right? Aging infrastructure, aggressive sustainability goals, and working with our utilities just to hopefully ride out some reliability concerns that we may or may not have. So with all this, we have our existing infrastructure, so we have to deal with how do we finance this, how do we integrate it with our existing infrastructure, and how do we bring in our operations folks to ensure that they're using the systems as intended to make it all work. So hopefully the session will bring you all some insight into some real world applications, and you'll have some good questions ready for our panelists. Let's see, sorry, I've gotta. And here are our panelists. We have Chad from UC Riverside, David Trombly from UC Davis, and Tony from UC Irvine Medical Center. So a little bit about each of them. Chad Sisco is the Director of Energy and Engineering within Facility Services at UC Riverside, where he supports campus modernization and sustainability initiatives. He's a licensed professional mechanical engineer in California and a lead AP. Beginning his career in 2004 at PTG, he spent 8 years designing HVAC systems and conducting energy analyses within a wide range of facilities. He later worked over 8 years with SCE as a field engineer, providing on-site energy efficiency, and also providing some demand-side management support for major clients. Combining design and field expertise, Chad now contributes to developing a smart, resilient, and energy-efficient UC Riverside campus. Welcome, Chad. Next, we have David. David Trombly is the Director of Energy Operations in the Utilities Department at UC Davis. In this role, he oversees both the high and medium voltage distribution, exterior lighting, backup generators, traffic lighting, and central heating and cooling. And he also manages purchasing and recharge of electricity and gas for campus. He previously worked for UC Davis in a different role as a data engineer and engineering supervisor, as well as in the private sector as a consultant. Welcome, David. And then finally, we have Tony Dover. Tony Dover is the Energy Management and Sustainability Officer at UC Irvine Health, where he champions the organization's vision for a more sustainable and resilient future in healthcare. As a strategic leader in energy efficiency, Tony drives system-wide initiatives that reduce carbon emissions, optimize operational performance, and advance sustainable design and infrastructure. With more than 18 years of energy management and sustainability planning experience, spanning state, county, and campus levels, Tony partners with clinical, operational, and facilities teams to embed sustainability into the organization's culture, ensuring that environmental responsibility supports both patient care and organizational excellence. And without further ado, we'll get started, and I believe Chad's first to present. And I'm gonna stop Chad, so you can show your slides.
Oh, yes, thank you. Here is everybody seeing my screen good?
Yes.
Great. Thank you. Well, thanks for having me, Michelle, and UC Davis. when you first asked me to present on my thermal energy storage systems here at UC Riverside, I was like, shoot, I don't really know anything about it. It's been here since when I was a kid, since the 80s and 90s. The plant was built when my mom was born in the 40s. So I essentially had to do a lot of research on history just to find out how it came to be. We have these 3 energy storage tanks on campus and 2 different plants, really. So the first part, I'll talk about, the past, how, UC Riverside even came to be. We weren't a campus, Riverside campus, alone in the beginning. We were part of an extension. Um, I'll talk about our past, and then I'll talk about our present and our future of the system. So for those not familiar, the city of Riverside is located beneath the San Gabriel and San Bernardino Mountains, and we were described as the birthplace of the California citrus industry, which is pretty cool. UCR started as the Citrus Experiment Station in 1907 as part of the University of California. But before that, since the 1870s in this area, where citrus was introduced, farmers were already looking for ways to combat disease, nutritional deficiencies, irrigation obstacles, frost, etc. So they asked for help in 1905, and by 1907, with $30,000, the UC Regents were moving into a 23-acre site located just west of here, near the base of Mount Rubidoux. In 1913, a freeze wiped out the crop that they were working on throughout this whole area, actually. And the citrus industry, valued at $175 million at the time, lobbied for additional research funding. I mean, go figure, you figure they could fund it themselves with that much money. Geez, in 1914, after multiple local counties in the area were considered for the new location, 475 acres over on the east side of Riverside was selected. And at the time, an interesting fact, this was such big news that the steam plant here, the electric plant, blew its whistle for 15 minutes, and they rang the mission in bells here over at the mission. So that's pretty cool. This site actually would eventually prove to be pretty advantageous for thermal energy storage, implemented decades later because of the hilly terrain that we're in. So really, over the next 30 years after that, it just grew both locally, in the community and the experiment station. And by 59, UC Riverside was declared a general campus by the UC Regents. So a little bit of history there. Our central heating and cooling plant was constructed in 1948, followed by a major expansion in 59. The central plant provided steam and chilled water to most of the campus buildings via a system of connected tunnels, which again was a great call at the time, because today we're going to be able to look at reusing those tunnels. But we do have some buildings connected to the central plant via direct buried pipe too. But up until the 80s, the plant utilized 2 steam turbine centrifugal chillers and 2 absorption chillers. One of the steam turbine chillers operated in series with the 2 absorption chillers as a piggyback design to take advantage of the condensing. But the other chiller had a surface condenser, which really derated its output, apparently, from 1,800 tons to about 900 to 1,100 tons. So in the mid-80s, they replaced 2 of the absorption chillers with new 1,000-ton 3-stage centrifugal chillers, which seems pretty fancy for the time. In the 80s, the train salesman was probably eating pretty good that night. But the upgrade to the all-electric chillers, combined with the recommendation to provide thermal energy storage, could be described as the first major energy efficiency retrofit at that time. So at that time, steam-derived cooling was more than 4 times as expensive as an all-electric plant during on-peak hours, and 8 times as expensive during off-peak hours, based on the rates that UCR was paying. So since the 80s, budget impacts similar to today made expansion and modernization of the plant pretty difficult. Also during this time, as I mentioned previously, UCR grew 87%, which necessitated an expansion of the central plant chill water capacity to meet those new loads. So they commissioned a study in 1989 by Brown and Caldwell, and it was a really good study. Thank God for Google that I found that study, because nobody here had any of this information. But I read through that study, all 400 pages of it. Um, and they really did highlight that fiscal restraint and financial and technical innovation was needed to mitigate these budgetary impacts. And the leadership at UCR took it to heart, and they concluded that combined with thermal energy storage, an all-electric chiller plant would save nearly $1 million versus expanding the continued operation of the steam-driven chillers. So after nearly doubling that enrollment growth, the 1990 long-range development plan projected increases again up to 18,000 by 2006 of enrollment. And at the same time, RPU, could only provide 9.8 megawatts at capacity. So in 1991, RPU prepared a survey of demand-side management techniques to reduce on-peak demand, and they collaborated to develop the thermal energy storage project, the very first one, to produce chilled water at night. The elevation advantage and the camouflage of the hills chosen, almost a century before, proved a perfect location for the tank, so that we don't have to worry about back pressure. They're installed higher than our tallest building, and you can't really even see them. They're mostly partially buried. You could really only see the tops of them. So the new tank eliminated the operation of the existing steam-driven chillers that were being replaced or being used at the time, I'm sorry, for on-peak cooling needs. And they were able to shift megawatts of demand to off-peak, which helped stabilize the local grid, which was growing at the same time here in the area. So although at the time of use tariffs were not opposed, provisions in the electric rate provided lower nighttime energy rates for customers using TES systems. So after plans were approved, TES-1, a 2 million gallon concrete chill water storage tank, was completed in 1995. So throughout the 90s, this is a diagram of pretty much our system today. This picture right here is a picture inside TES-3 when it was being constructed that I found on our website. But throughout the 90s, the relative low cost of energy made efficiency efforts pretty unattractive financially speaking. The only major improvements included replacing those two steam turbine chillers with the new all-electric chillers. It wasn't until the early 2000s when we doubled enrollment again to over 15,000 that they took advantage of some new energy efficiency incentives to install the second TES tank. And they also had plans for the satellite chilled water plant, which was a new plant at the time, and a third TES tank. So in 2000, they began some retrofits at the steam plant. They replaced all 5 cooling towers. They installed a new 20-inch chill water pipe that connected essentially the north side of campus to the south side of campus. And then eventually that would tie into a new 24-inch chill water loop over here on the east side of campus where it runs. The central plant is right here in the center of campus. So after they did that, around 2005, our second thermal energy storage tank was installed. TES-2 is 2.7 million gallons, capacity about 24,000 ton hours. And it was also tucked into the hills into the south here. Here's TES-2 and 3, and here's TES-1, if you can see my little cursor on the screen. TES-3, well, at the time when they built the satellite plant, they built to built it out for 4 chillers, but only installed 2. They installed 2 2,000-ton duplex 2-stage centrifugal train chillers in a primary secondary configuration. And with that setup, at least, UCR could produce chill water now from 2 different plants, 2 different tanks simultaneously or independently, whatever the load demanded. It was pretty flexible. It was a pretty nice design to add that satellite chiller plant. And then a decade later, in 2013, TES3 was finally installed adjacent to number 2, and the satellite plant received its 3rd duplex chiller and tower. So TES3 is slightly smaller at 2.2 million gallons and has a 20,000 ton-hour capacity. It wasn't until 2016, as I mentioned earlier, that RPU implemented time of use rate structures, and demand charges appeared on the bill for the first time. That was a $60K hit they took on that bill that I looked at. And yeah, they were like, what do we do now? So there was no energy department at the time. They hired some faculty and staff to kind of get the ball rolling. They installed some sub-metering at buildings, got that kicked off and started. And then in 2019 is when they actually created a department and started hiring engineers. So since then, we work to install metering. Man, we have almost 50 core buildings metered. We've already worked on energy efficiency projects in more than 15 buildings, saving 5 million kilowatt hours of electricity, 8,000 MMBTU of natural gas, and 1,400 metric tons of CO2. So most recently, we completed the study to explore what it would take to decarbonize the campus as everybody else did. So our next phase, excuse me. Our next phase is to expand the satellite chiller plant once again. This is in alignment with our recently completed decarbonization study, which outlined the need to expand the satellite chiller plant in order to take equipment at the steam plant offline for future replacement, utilizing heat recovery chillers, heat pumps, and the like. We've also completed, we've almost actually completed this design. I think it's at 90% CDs for the 4th chiller and 4th tower. That'll bring the plant up to 8,000 tons of total chiller capacity. And we're also taking the time to retro commission TES3 because it's never really been able to operate independently in discharge mode during the peak demand. It just can't flow enough GPM to meet the peak by itself like the other 2 can. So what I did find is that value engineering at the time reduced the internal diffuser system to that point. So we're going to go back in, hopefully retrofit that diffuser system to match TES2 so it can flow and it can work, in parallel, independent as needed, as designed, actually. So once complete, our chilled water system will have a total of over 14,000 tons of chiller capacity and over 60,000 ton hours of storage, chilled water storage capacity, which is great. So an assessment of our existing UCR hourly demand data during the decarb study found that simultaneous heating and cooling occurs more than 70% of the time, which we knew it occurred, but not at this rate. We didn't think 70%, which was great, right? It almost is similar to Stanford in that respect, where heat pumps will make a good energy impact in the campus. So during typical operations, our satellite plant serves about 80% of the campus cooling needs, and the steam plant handles the remaining about 20%. So we've been looking at additional upgrades at the plant, including secondary chill water pumps, because they vary speed based on a single differential pressure location near Bournes Hall, which is a building out on the north side of campus. We analyzed the loop and modeled pump control at various different sensor locations and found pretty good savings from optimizing the pump speed based on some alternate locations. So we're moving forward with that. We're also targeting lab energy efficiency improvements, including exhaust fan retrofits with variable frequency drives, airflow optimization to reduce air changes, and occupancy-based controls, reduce fume hood airflows to minimums. So a lot of this stuff is low-hanging fruit because, like I mentioned before, we've never really invested in energy efficiency because financially it never really made sense because of our relative low cost of electricity from Riverside Public Utilities. So, you know, today we're find ourselves almost doubling enrollment again. We set a new record this year, more than 27,000 this fall. So with campus capacities, I mean, we're nearing our peaks once again, as history showed. It's usually when we hit these enrollments, and we're very reactive, as you can tell. We wait until we have no capacity left to act. So to no fault of anybody's, but it is what it is, and that's what it's been historically. So moving forward with decarbonization, a total of 5 major scenarios were explored in our study compared to the business as usual scenario. Some of them included variants. Scenario 1 involved electrification of the existing steam plant enabled by building and distribution transitions from steam to low temperature hot water. The variants 1.1 and 1.2 are just with and without hot water thermal energy storage. Scenario 2 studied breaking the central plant into heating districts across the campus. 3 looked at electrification of the steam boilers. 3.1 and 3.2 compared electric boilers versus heat pump. Scenario 4 explored alternative fuel options, including biomethane and hydrogen. And 5 studied the actual decentralization of the campus and electrify it at the building level. But after consideration, our preferred option is scenario 1.2 heat pump technology with hot water thermal energy storage, if you guys reference our study. So I won't go into this study too much here. But evaluation criteria for the study included GHG emissions reduction, life cycle cost, annual peak resource use, resilience and reliability, ease of implementation, and a few others. In our preferred scenario, steam building systems would be replaced with low temp hot water, requiring heating coil, pipe, pumps, heat exchanger replacements in a phased approach. And the heating hot water TES system combined with heat pump technology is expected to increase the plant efficiency to a CEOP over 5. So our plan is to also keep 1 or 2 of the natural gas fired steam boilers coupled with a steam to hot water heat exchanger as a backup source of hot water. So it's good to hear that recommendation earlier as part of maintaining reliability because we were intending to do that also. Also makes sense to plan to utilize it if you're going to pay standby tariffs for your rate, which I don't even know what a SoCal gas standby tariff looks like, and I wasn't able to get that from anybody. So we're currently creating the scope of work for the first phase of decarbonization, which will include removing a section of 8-inch high pressure steam lines that run to the east and installing some main plant equipment like the heat exchanger, the pump station, and some piping. So that is pretty much it.
Thanks, Chad.
Our TES in a nutshell.
Thanks, Chad. We'll wait to the end to kind of do the Q&A, but maybe we can transition to David's presentation.
Okay, great.
David, you ready?
Yes. All right, is everyone able to see that? Yeah, okay. Just make sure I can advance the slides. Okay. Good afternoon, everyone. Thanks, Chad. UC Davis also has a thermal energy storage capacity, and so I'm kind of maybe Chad's kind of talked more about sort of history and kind of construction and plant configuration. I'm going to focus a little more on kind of utilization of the resource and how we're doing that at UC Davis, and specifically dispatching it in our variable electricity price context. So a little background. We have two cooling plants. We call it the central cooling plant. Has four 2,500 ton chillers, and then we have a separate nearby but different place thermal energy storage plant, which has four 2,000 ton chillers. And then that site also has a 5 million gallon cold water storage tank. So we're able to store the cold water, and then you run from the tank when we want to, and then the tank also has the potential to provide kind of peaking capabilities if we fill it. If we need to run all our chillers at the same time and we still need more capacity, we could also run from the tank. So those are kind of the benefits of the tank. Just for context, the estimated power cost of this equipment is about $2.3 million per year. That's just basically electricity. So that'll be helpful to keep in mind as I start to look at some of the savings that we're achieving with some of our dispatching work. And then just another context item, we have a pretty large renewables footprint on site behind our meter. This is a picture of our large solar farm in South Campus. It's on 62 acres of campus land. It's behind the meter, so that means all of the production from that is used by the campus. We don't export anything, so that's a 16.3 megawatt DC installation. And then we also have various rooftop systems that are about 204 kW, and then we have a large P3 housing parking lot installation that's another little almost 800 kilowatts. So kind of going from that, what I'm showing here is basically the campus load shape. This is a June 21st, 2016. So this is soon after we installed that really large 62-acre facility. And so you can see the kind of beige line is the production of the plant. It's a tracking system, so it kind of goes flat kind of in the midday. So somewhere around 13 megawatts. And then you see kind of the stereotypical duck curve pattern with our blue. That's like kind of our net of solar take from the grid, where it kind of goes down during the day due to the solar, and then kind of comes back up in the evening hours. So I mean, there's kind of, just from the perspective of renewables utilization, there's kind of motivation to shift our load somehow, to kind of get some of that peak usage over to kind of the time when the solar is producing. And then another driver is just our rate structure. So this graph shows one thing. There's a little bit of sleight of hand here in terms of me showing the demand curve from 2016. The reason I showed it from so long ago is that currently the solar facility is somewhat underperforming. So it's a little more compelling to show the 2016 load shape, but provided we can kind of work with the owner, PPA owner, to get it better performing, we should see that duck curve emerge again. And then this price structure is from more recent. This is July of this year. And we're basically subject to the wholesale market. So the orange is our day-ahead market price, and then the purple is the real-time market. I can go into more details of exactly how our costs are settled, but the motivation basically is that if you look at this, the blue and this, basically we're peaking at the same time as our price goes up. And that's kind of a daily occurrence, basically. So that's kind of the motivation for our work. And then, so kind of getting to our solution and how we implemented better dispatch of our TES system. This is just kind of a flow chart of how we did this. It's basically an optimization algorithm. We worked with some researchers in the Department of Chemical Engineering and also someone from the Energy Graduate Group to build an optimization algorithm to dispatch, to kind of recommend to operators how to dispatch the thermal energy storage tank along with the chillers. A couple key highlights. We have the Pi system. It's a real-time data system. I think a lot of folks probably use SkySpark in this capacity. We have a little bit of a larger utility system, so we are able to justify a little more of a industrial scale system. And then kind of looking to the upper right, we're basically using an API to get real-time weather forecasts. Kind of looking around to the left, we're getting also our electricity price signal, and then also from our control systems in the lower left, getting information about our chilled water system as well as our electricity use. And then all that kind of looking kind of back to the upper right kind of goes into a prediction that we're making. We have data scientists who are predicting our future demand, and then an optimization algorithm that's written in Python that basically spits out like when should, at this time, should I be running the chillers or not, essentially. And then that's kind of put back into our Pi system so it can be visualized. So, and then, to the kind of the lower right, this Pi Vision, that's sort of the visualization scheme we have, and I'm going to show you details about that. This is like our operator screen that we built in Pi. The rows are the different chillers, basically. So one, you can see to the left, 1, 2, 3, 4, B1, B2, C1, C2. Those are the chillers. And then the columns are hours, basically. And then you see there's a little gray box at 12 noon. So that's the present. So basically what this is showing is what they should be doing in the current hour. And then to the left, it's actually showing how they performed. So like the purple means that I think they should have been running, but they weren't. And then the red is they shouldn't have been running, but they were. And then kind of the blue off to the right shows how they're expected to run in the future. So this is kind of a visualization of the results of our optimization algorithm. You can also see the rectangles at the top showing for that particular day the projected price. So they can see that. And then down toward the lower left, you can see how full the tank is, that 91%, as well as kind of projected tank capacity there at the bottom. And also the demand forecast. The blue is the tank capacity, the orange is the campus demand forecast. So basically, we're at a point where this is a recommendation to the operators to tell them how we think they should be running. In this particular hour, I think what's happening actually is that they're basically running B1 instead of B2 for some reason. You see, so B1 is red and B2 is purple. So I would call that kind of no harm, no foul. There may be reasons in the optimization algorithm where we plug in equipment efficiency, and so there might be a slight preference for one or the other, but in this case, there may be operational reasons that override that. So I'll talk a little bit more about the algorithm in a bit when I kind of talk about challenges, but that's the basic thing we're doing. In terms of results, well, so one other thing to note is that this is a nice communication tool with the operators. We worked with a user experience designer to kind of there was a lot of like extra stuff that was on here that it seems like they weren't using. So like the user experience designer who's also been involved in the thermostat and seed dashboards, Kiernan, she kind of interviewed the operators and helped us, kind of optimize the user experience, which it was pretty valuable skill set and process, I would say. Yeah, and then we can also, I think in the next slide, I'm going to show you kind of how we had some demand response program results that we also did. So that's more of in general, we're sort of dispatching this tank day by day to try to optimize it with our wholesale market price, but then there may be times where there's events that are kind of more high stakes, and so we may kind of turn more stuff off during an event. I think at the time, the biggest bang I'm going to show you in a minute, it was in 2022 during the kind of heat storm events. I think at that time we had to like manually change the ones and zeros in the back end to to get the screen to show what we wanted, but I believe subsequently we've kind of like modified the code so like we can read in an event more automatically. Anyway, during that heat storm in 2022, you see this is early September 2022. Let's see. So the red is total campus power, and then the orange, that's kind of second from the top, is the chiller plant power. And then the blue and purple are our prices. The blue is the real-time price, and the purple is the day-ahead price. So you can see basically, like, if you look at the orange, we're turning most of our chillers off at the times when the power is peaking. And then there was also kind of, that's wholesale market savings, but then overlaid on that, there's also some demand response program savings we got. So we provided 91 megawatt hours of demand response in that time frame. So it's about a 5 or 6 day time frame. So that's maybe like 15 megawatt hours per day, maybe something like that. And then another kind of looking at cost savings in general, we estimate that our kind of wholesale market dispatch that we're doing is saving us about $150,000 a year. Again, keep in mind the kind of about $2 million equipment cost. And then since we started the demand response stuff in 2022, we've made $635,000 from that. So pretty good results, maybe 10% equipment cost reduction, something like that. And then another kind of benefit is that with the researchers, we published a paper kind of showing their work in applied energy. So as I kind of finish up here, I'm going to talk a little bit about some of the challenges with this optimization algorithm. This is something that we could talk about more later in the questions if that's helpful, but a lot of these kind of came into like the optimization algorithm has certain constraints that we've put in. So like you're kind of penalizing certain actions. So one action we're penalizing is like prevent frequent changes of on and off, frequent on off of equipment. So I think you're required to, once you turn on a chiller, you're required to keep it on for 4 hours. And so then that's built in. So kind of like figuring out those constraints has been somewhat challenging. And sometimes like constraints can kind of fight each other. So kind of a related thing for the second bullet is similar to a battery. If you're going to utilize the tank for dispatch, you don't have it for backup. So the operators have comfort level obstacles with respect to draining the tank below a certain percentage. So that's kind of something that we've had to work on. I think right now we're constraining the tank to always have 10% capacity, but those things can kind of be at odds at times. Another thing we've struggled with is like having an accurate demand prediction and having accurate weather forecasts. We've kind of worked through that. And then another decision kind of consideration is whether we wanted to do full automation versus kind of more of an operator recommendation. Right now we're doing the latter. To me, it seems like that's probably the optimum, and I think this is probably the case with a lot of machine learning or AI type applications, like the final 5% to get to fully autonomous operation may not be worth it, maybe too difficult. It's better to have like a human mediated situation with a recommendation using, AI or whatever. Operator trust. Sometimes equipment, that's a big one, like getting the operators to trust it, equipment downtime. Sometimes presented challenges. And then also we've kind of worked through how to run during the winter, whether we should continue optimizing or do something like we also can kind of like repump our TES tank with hotter water and pump it through again and run it through the campus again. And is it better to optimize or repump? So those are some challenges. And then just a little bit about kind of current work. We're now part of like a capacity-based DR program. And so we're working on understanding the cost signals of that and optimizing our participation. And then another future challenge is that, as been mentioned, we're electrifying our heating system. So those are going to be coupled systems, and we're going to have to kind of redo our optimization to include that heating. That's all I have. Yeah.
Thanks, David. Pretty thorough
Good.
discussion. We're going to round it out with Tony from UC Irvine Health. And then after that, we'll have a few minutes for questions. So thanks, Tony, for round us out.
let me know when you can see. Okay, you see my screen?
Yeah. Yes.
All right. Good afternoon, everyone. So I'm going to talk to you a little bit about our battery energy storage system at the UCI Health Orange campus. The location is an old generator. It's installed in an electrical yard next to a parking structure in our electrical distribution building. The electrical yard is enclosed in a concrete area with no roof. Its previous the previous use of this space was for 3 diesel generators. They were 40 years old. That were decommissioned and removed under a new chiller plant project. We had a feasibility study done for our project for installing and looking at where we could put in battery storage on the whole campus. And this site was ideal just due to the proximity next to the utility tie-in. And then the electrical infrastructure is really close by. It's outdoors, protected away from the public view or patients coming in and out of that parking structure in the area. So it was an ideal location. So the project is 1.9 megawatts. We did it. The driver was really just peak load shifting strategy to reduce our energy bill cost through our demand charge reduction. The forecasting software predicts demand spikes and switches the buildings from grid to the battery power. And the battery discharges, during peak hours when the power is expensive. And then it charges at night when the cost of the grid is low. This battery system discharges for 4-hour duration. There are 46 Tesla power packs. The project was completed in August of 2020. And so the procurement method, how we implemented the system was through a utility program. We're located in the West LA Basin. This is a capacity constrained area. And so SME created, that's the utility here in Southern California, created a program called the LCR program, the local capacity requirement, which basically awarded AMS, who was a battery storage developer, a 50 million megawatt contract to bundle energy storage systems together and act as if a virtual power plant. And so you could store up energy and then use it during high demands in the area. The contract is an energy management service agreement, or an EMSA, and that is a 10-year contract that we have. It's similar to a PPA that has a site license, but it has a service agreement. Rather than purchasing power, we're paying a service charge. And so we as UCI Health receive the cost savings through the operation of the system, and then we pay a management firm a monthly fee of about $2,000, so about $24,000 a year for maintaining and operating the batteries. So there was no upfront cost to us. It's a 10-year term. We also included a guarantee performance in the contract. And we have 2 feeds that come into this campus. And it reduces the demand about 15% on one and about 10% on the other meter. And the end of term contract, I mean, the terms and options at the end of the contract, we can extend the contract itself. We could have them decommission it and completely bring the site back to its original, or we can buy them out and buy the batteries and negotiate a price with the owners. So I've mentioned already about, these are just some additional benefits of the project. And this is a couple pictures of the installation. It's an ideal site, better use of the space. Also, we discovered during the construction that there was contaminated soil due to, diesel generators running on the site for over 40 years. So we had to, part of the agreement cost was testing, excavation, and remediation of the contaminated soil. It was all covered, and no cost to UCI Health. Another advantage to the project was that the electrical infrastructure, as we started to process the interconnection agreement for the batteries to the utility grid, they required an upgrade. And so the contract also covered the cost of all the equipment. We added a primary meter cabinet. We removed a lot of old equipment. And then the contract included them paying for 10 years of operation, maintenance, and any replacement coverage cost for the electrical infrastructure. To date, as far as the performance, overall, it's been performing, pretty well. One benefit though is having the guaranteed performance numbers in the contract, which for this project is $136,000 that we are guaranteed to save every year, and they have not met that yet. So we've had a shortfall check every year, so we know that we can at least get that minimum of $136,000 savings for the system. It was down in 2023 due to a switchgear. And I don't know if you remember at the time, but getting a switchgear a couple of years ago, there was like a lead time of a year. So they ended up procuring components and replacing what was needed and getting it back up and running. But it was down over the summer, which that's when the demand charges are at their highest rate. But overall, the project has performed well. And it really is kind of like a PPA, so it's a black box in the sense that we don't have any control over when the system charges or discharges. They do charge on the grid after midnight and before 4 a.m. When our prices are low and obviously our demand is low on the campus. And that's pretty much all I have.
Thanks, Tony. I hope everyone enjoyed hearing kind of the variety of presentations related to both thermal and electrical energy storage. I think there's only one question, so don't be shy, everyone. If you want to pop some questions in the Q&A, that there was one question directed to Chad about your blended rate. And Kenny said, props for an amazing story. So what do you know your blended rate? If you don't know it right now, I guess if you find it out, you can message to Kenny.
At what point of time?
Kenny, you can unmute and ask the question directly, or you can type it in. I think he just means on average, what's your blended
just on
rate?
average, yeah. Okay, so today, around 13 cents. Back then, I think the 80s, when they were looking at this, it was 6 cents.
I was going to say 7. So yeah, okay.
and they had a off peak option, which was like 2 or 3 cents. So
wow.
Yeah. So
okay. Thanks, Chad.
Kind of actually an interesting question. I'll just chime in since we have a little time. One thing Chad and I kind of talked about as we were preparing for the presentation was that the sort of operational mode is impacted a lot by the rate structure. So I think, Chad, you're just basically Riverside is just basically trying to avoid peak, right? But we have more of a hourly pricing, so it's kind of different strategies.
A little more dynamic. And David,
Yeah, I mean,
having
yeah, but and then they have their capacity allocated to essentially avoid the peak period.
Yeah.
I don't see, yeah, they're just kind of, it's just interesting how different rate structures result in different strategies.
Yeah, with the flat rate, it was just, essentially all hands at deck at night, make as much as you can, and then during the day discharge and serve the load. And rinse and repeat each day. Just stay out of those on peak. And that's it. That's what we do still today.
I have a question actually for Tony, because I thought it was creative, that creative strategy of procurement. And I messaged you last week, Tony, about this, like any advice to campuses who are kind of entering maybe some of that creative strategy of, and especially in contracting, right? So if we don't have an EMSA, but you said it's like a PPA, so maybe a lot of us are somewhat familiar with that, but do you have any advice on how to kind of navigate that? And who to pull in maybe from whether it's contracting or your planning department? Yeah.
We had a large group of stakeholders because it was the first time we were going through this type of a contract. Also because it was a 10-year term, you have to get UCOP involved, and so there's a process for them to review and approve. So they were a part of the stakeholders team, but we had capital planning, we had facilities, and then we had our legal team here at the local level, and then there were a couple representatives from the UCOP level that were on the team, and reviewing contracts as part of the negotiation of the overall contract. I would suggest having a guaranteed savings. I've been through a couple PPAs, some that didn't work out well. This one has been working out fine, but I would definitely have a guarantee in the contract, like whether that's whatever kind of performance that is, and be pretty detailed and flush that out.
To piggyback on that, Tony, not only a guarantee, but in our PPA, there's a guarantee, but they limit the max.
On the other side.
Yeah. So
Yeah.
they don't, their guarantee is they'll give you some funds based off what they don't produce on what they projected up until a certain cap. So look
No,
for that
we
too.
don't, yeah.
Few more minutes. If there aren't any other questions. Oh, we do have some Q&A. Tony, this is from Ben at SF. Tony, they charge at night. Why not during day? Also, why power walls and not Megapack?
I only got part of that question about them. They charge at night because that's when there's less demand over here is at night and lower cost. And during the day, our peak actually on this campus is about noon. So it's not later in the afternoon when the higher rates, higher peak demand charges. So that's why it's at night.
And the second part was about, I think, because you showed a picture, why power walls and not Megapack? I think it's referring to the Tesla.
The Tesla power pack. It was the power pack 2.5. I thought that's what we have. And then they were asking why we didn't use power walls.
I think it's a reverse. I think he thought it was what you had,
Yeah.
power walls. Maybe just.
No, we have the Tesla power pack 2.5s.
And just sorry, I can't use Q&A, I think, because I'm a moderator or something. But just to follow up, Tony, how far are you into the PPA, and are you considering buying them out at the end?
Yeah, good question. We've had a lot of conversations with the decarbonization study completed and looking to the future. We want to put about 5 more megawatts on this campus of storage, as far as that's in the study. And I think we've looked at a couple of the scenarios, and it really will depend. Like it's such a dynamic market and moving forward. I mean, what we decide today, if we're 5 years into a 10-year, that we're going into our 6th year of a 10-year term. And so it's 4 years before we have to make a decision, probably 3 years with 12 months ahead. And I could see, they've already approached us, the owners, 3 times asking us to extend. And we've denied because I think we can get a better system, and I think we could, we want to control it a little more. One of the downsides is that we can't participate in some of the demand response programs. So I think, but we have a pretty good site now, and if we have them come in and completely clear it out, we have a great site to just plug and play whatever is the newest and greatest system.
Any other questions? I think we have until 2:05, but doesn't mean we need to take until 2:05.
Looks like there's one more in Q&A
Let's see.
from Sozi.
From Sosi, have you used it for emergency backup? I presume he means to Tony, but maybe not. All you. Emergency backup.
We don't have control over it to use for emergency backup while it's not in our control, so.
We've never shifted our operation unless requested. As far as demand response goes, RPU is not IOU, so they don't participate in the statewide demand response program. So historically, in the summer, they said, "Hey, UCR, can you shift your load?" And we said, "Yes, we can." But then we just take the demand hit for that month, and historically have never been compensated for it until recently. Last year, we were able to sign up for a third-party demand response program. So that'll be good.
I guess since we're talking about emergency backup, if that's a question for everyone, we would be able to use our TES tank for emergency backup if the pumps were backed up, but I don't think they are. Maybe that may be something we do eventually, but yeah, I guess a chilled water outage it could accommodate, but a power outage we would need backup for the pumps.
Right.
And one other kind of follow-up, Chad, to what you said. I believe you correct me if I'm wrong, but I think UCR is the largest customer of Riverside Public Utilities. So you guys get to really kind of work hand in hand, and you have a lot of say in kind of how you can help them out or not with those units. And so you're in kind of a really special position with your utility there.
Yep. Yeah, I mean, there's some competitors move into town over the years and back out, but yeah, our stability leads to a pretty good relationship with them.
I think we're going to end early and hand it over to Maria.
Yeah. Thank you, Michelle.
Thank you all, everyone, for their presentations.
Thank you so much. You guys are actually perfectly on time. So thanks, Michelle, for guiding the panel and keeping things on track. And thank you, Tony, David, and Chad, for such an insightful session on energy storage programs on your facilities. We've addressed some questions, but in case anybody has any more, please go ahead and put them in the Q&A box, and the speakers can address them as we go on.